Hello everyone, my name is Ela Bursalı, and in this video I will be explaining topic 1.1 as you can see in the picture. So topic 1.1 is the introduction to the particulate nature of matter. So this is the first topic for IBHL chemistry, and in this topic we will explore one of the most fundamental ideas in chemistry, which is the idea that all matter is made up of tiny particles called atoms, which are made up of tinier particles called maybe protons, neutrons, and electrons. So understanding this concept will help us to explain physical states such as liquids, solids, gases, and changes of states, which is from liquid to solid or from solid to liquid, diffusion, and also many other observable phenomena in chemistry and even in physics as well. So this topic forms the foundation for everything we will study later in chemistry, because in this topic we will learn the definitions of very simple chemistry terms. And I want to start by asking a simple question, which is, what is matter and what is it actually made up of? So as you can see in this table right here, matter is divided into two sub-levels. The first one is pure substances and the second one is mixtures. So let's start with pure substances. First, elements are pure substances that are made up of only one type of atom. So in an element, there is only one type of atom, no more than one. This means that all particles in the substance have the same number of protons, and the protons, which is the atomic number, defines the elements. So simply to sum up, elements cannot be chemically broken down into simpler substances because they are already in the simplest form of matter chemically. As I said, an example we can give to elements could be oxygen, O2. So it only consists of one type of atom. It has a fixed ratio, fixed composition. It's represented by a chemical symbol, which is O, the notion, like the chemical symbol for oxygen, and it cannot be broken down into a simpler substance by any chemical means, so it's an element. The second example could be, again, a very simple one, helium, maybe. It's again in the periodic table. It's on the 18th group. It's in the first period. It's a noble gas, and it cannot be broken down into a simpler substance because there's only one type of atom and also a single atom. So yeah, it's an element. Another type of element could be giant structures. For example, carbon and diamond or graphite. So carbon could also be an element because it has a fixed ratio, and also it's a single atom. It has only one type of atom in it. So these could be the examples for elements. Secondly, compounds. So a compound is a pure substance, again, because it's under the topic of pure substances as well as elements. So these are pure substances formed when two or more different elements are chemically bonded together in a fixed ratio. So I think the keywords for compounds should be a fixed ratio, two or more types of atoms, and chemically bonded. So the key idea is chemical bonding, because the atoms are joined by strong forces, ionic or covalent, which will be discussed in 2.1, 2.2, and a chemical reaction is required to separate them. So compounds have two or more different elements, different types of elements, and they bond with chemical bonds, and a chemical reaction is required to separate them. So this is the main idea of compounds. And the properties of a compound are completely different from the properties of elements that form it. So For example, think of water. It's H2O. Water has different properties than hydrogen and oxygen. Just because water is composed of hydrogen and oxygen doesn't mean that it has the same properties of those two elements. So for this example, I can further explain it. Like hydrogen is flammable. Oxygen supports combustion, but water is used to extinguish fire. So that's why in a compound, the elements that form this compound have completely different properties than this compound that they form. So to sum up, some key characteristics could be for compounds, they have two or more than one type of atom, in contrast with elements which had only a single type of atom, as you can see in these examples as well. The atoms are chemically bonded, so the hydrogen atoms and oxygen atoms in this example are bonded with hydrogen bonds, so they are chemically bonded and they need chemical reactions to separate them. They have a fixed ratio, so this is also important because you can't express water as H4O2 even though the ratio is the same. So it has to be in the empirical formula. So yeah, they have a fixed ratio and they have a chemical formula, as you can see from water, H2O. And other examples could simply be CO2, carbon dioxide, and sodium chloride, maybe NaCl. So these are also bonded chemically. So now let's come to mixtures. First, I want to talk about homogeneous mixtures. So a homogeneous mixture is a mixture where the composition is uniform throughout the entire sample. So the keywords is uniform for this. This means that every part of the mixture has the same proportions of substances. So in contrast with compounds, in homogeneous mixtures, the substances are physically mixed. So what this means is that they're not chemically bonded. But in compounds, there were chemical bonds between atoms. But in homogeneous mixtures, the substances are physically mixed and there are no chemical bonds. Therefore, they retain their own chemical properties. Homogeneous mixtures are also commonly called solutions. And even though it looks like one single substance, homogeneous mixtures are still made up of different particles mixed evenly at microscopic level. So that's why homogeneous mixtures are seen as uniform and you can't distinguish the substances inside this mixture with naked eye. And this is the most important properties that you have to know about homogeneous mixtures. The examples I can give are salt dissolved in water. So think about this. Salt is dissolved in water. It can be dissolved in water when you mix them physically. And when you look at a salty water, you cannot distinguish that there is salt in that mixture with your naked eye. So that's why this is the most common example of a homogeneous mixture. The second one could be air, which is made up of a mixture of nitrogen and oxygen. But when you look at air with your naked eye, you cannot distinguish that there is nitrogen and oxygen atoms in the air. So it's a homogeneous mixture. And the last example I could give is brass, which is made up of copper and zinc alloy, which is also a homogeneous mixture. So now let's come to heterogeneous mixtures. A heterogeneous mixture has a non-uniform composition. So the keyword for this is non-uniform. The different substances are not evenly distributed, in contrast with homogeneous mixtures, in which the substances were evenly distributed, and you couldn't distinguish these substances with naked eye. And in heterogeneous, again, in contrast, you can often see the different phases or components. These substances are still only physically combined and can be separated by physical methods. So, to sum up, the key characteristics of heterogeneous mixtures are that they are non-uniform, the different parts or phases are visible, they are again physically mixed, and they can be separated by physical methods such as filtration, decantation, and those types of separation methods. And examples we can give to heterogeneous mixtures are oil and water, which is the most common example because if you mix, oil and water doesn't mix, and a heterogeneous mixture of oil and water, you can distinguish the oil and water with naked eye, so it's heterogeneous. Again, sand and water, same, you can distinguish the sand inside the water. And another simple example could be a salad, because a salad, you can distinguish the tomatoes, the cucumbers, the lettuce, and all of that in a salad, so it's simply a heterogeneous mixture. So this is mainly what matter is. So it's mainly, in detail, divided into four, as I explained: elements, compounds, heterogeneous mixtures, and homogeneous mixtures. Okay, so now I will continue with how kinetic energy relates to the changes between solids, liquids, and gases. So as you can see in this page, solids are particles that are closely packed together. So the atoms are very close and closer together. So this makes the interparticular forces strong and particles vibrate in their position. Solids have fixed shapes and fixed volumes. So a pencil, it has a fixed shape and it has a fixed volume. The other model could be liquids, which are more spaced than solids, as you can see in this image right here again. Their interparticular forces are weaker than solids because they have more spaces between their particles, and these particles can slide over each other, so they don't have a fixed shape. For example, if you pour water, which is a liquid, into a glass, it will take the shape of the glass, and but it will take the shape of a glass, but they have a fixed volume, so its volume will not change. Because it's fixed. And lastly, gases. So the particles are fully spread out, as you can see again right here. The inner particle forces are negligible because the particles are fully spread out and they have a lot of distance between them, and the particles move freely, so they are free and they are mobile. They don't have a fixed shape because, again, as liquids, if you put them in a container, they take the shape of a container, and they don't have a fixed volume, in contrast with solids and liquids. So from solids to gases, the temperature increases, and what I mean by temperature is average kinetic energy. So if you want to define temperature, you should say that temperature of a substance is directly related to the average kinetic energy of its particles, because kinetic energy is the energy of motion. So why does temperature or kinetic energy of particles increase as we go from solids to liquids? Because solids are closely packed, but gases are fully spread out, so they are more free to move. So we defined kinetic energy or temperature as the average kinetic energy, and kinetic energy as the energy of motion. So if a particle or if a substance, particles are more free to move, then their kinetic energy will be more. That's why in a solid, particles have the lowest kinetic energy. So if heating continues, the kinetic energy increases because the temperature, thus the motion of the particles increase. However, at the boiling point, so if we draw a graph right here, this is, like this. So this is the melting or freezing point. This is the boiling point or condensation point. So as the heating continues, the kinetic energy increases even further because the temperature increases. And at the boiling point, as you can see right here, the particles have enough energy to overcome the intermolecular forces almost completely, forming a gas. So that's why a boiling point takes more time. So this part A and this part B, A is bigger than B because in boiling point, you have enough energy to overcome the intermolecular forces almost completely, so you break the bonds completely and form a gas. And to sum up, from solid to liquid to gas, kinetic energy increases. So like as you go from solid, liquid, gas, the kinetic energy increases because the temperature increases. In the opposite direction, from gases to solids, as you can see, the temperature was here, now it's here, so temperature decreased, so the kinetic energy decreased.